Hello everyone, my name is Utsav, and I'm a city planning student at IIT Kharagpur. In this video, I want to talk about density-based clustering. Density-based clustering is a powerful technique used in machine learning to identify clusters in data based on their proximity and density. In city planning, this technique can analyze urban data and identify patterns and relationships between population density, land use, transportation, etc. By using density-based clustering algorithms, city planners can make more informed decisions about allocating resources, planning infrastructure, and designing urban spaces that are more responsive to the needs of the people who live and work in them. So, let's dive into density-based clustering and see how it can be applied to city planning. Clustering is the process of grouping similar objects or data points together. Density-based clustering is a type of clustering that groups together points based on their density in a given space. It identifies areas of high density as clusters and areas of low density as noise. Density-based clustering is an important technique in machine learning and AI systems as it allows for the identification of patterns and structures in large datasets. It can be used for a wide range of applications, including anomaly detection, image segmentation, and recommendation systems. Density-based clustering is typically used in the classification stage of AI systems. It helps to group data points into different categories or classes, which can then be used to train machine learning models. Key concepts in density-based clustering. 1. Density. Density is the measure of how many data points are located within a specific area. In density-based clustering, a cluster is formed by a dense region of data points, which are close to each other in terms of their distance to distance. Distance is a measure of how far apart two data points are from each other. In density-based clustering, the distance between two data points is calculated using a distance metric such as Euclidean distance or Manhattan distance. 3. Core points. Core points are data points that have a sufficient number of other data points within a specified distance, known as the density radius. These core points are used to form the basis of a cluster. 4. Border points. Border points are data points that are within the density radius of a core point but do not have enough neighboring data points to be considered a core point themselves. These border points are included in the cluster formed by the core point. 5. Noise points. Noise points are data points that are not close enough to any core points to be included in any cluster. These noise points are typically discarded in density-based clustering. 6. Differences from other clustering techniques. Density-based clustering differs from other clustering techniques in that it does not require a predetermined number of clusters to be specified. Instead, clusters are formed based on the density and proximity of the data points, allowing for more flexibility in cluster formation. Additionally, density-based clustering is better suited for non-spherical clusters and clusters of varying densities. Advantages of density-based clustering. Density-based clustering has several advantages over other clustering techniques. One of its key advantages is its ability to handle noise in the data, which can be a major issue in other clustering methods. Density-based clustering is also flexible in detecting clusters of various shapes and sizes and does not require prior knowledge of the number of clusters. Density-based clustering has been successfully used in a range of real-world applications. For example, it has been used in traffic flow analysis to detect areas of congestion and identify traffic patterns. It has also been used in environmental studies to detect clusters of pollution and monitor air and water quality. In addition, density-based clustering has been used in customer segmentation to identify groups of customers with similar purchasing behaviors, and in anomaly detection to identify unusual patterns in network traffic or financial transactions. Density-based clustering works by identifying areas of higher density within a dataset and using these areas to form clusters. The DBSCAN algorithm is commonly used for density-based clustering and has two main parameters, epsilon and minimum points. 1. Epsilon. Epsilon specifies the maximum distance between 2 points for them to be considered part of the same cluster. 2. Minimum points specifies the minimum number of points required to form a cluster. The DBSCAN algorithm works by starting with a random data point and identifying all neighboring points within epsilon distance. If the number of neighboring points is greater than or equal to the minimum points parameter, a new cluster is formed. This process continues until all points have been assigned to a cluster or labeled as noise. Data preprocessing is a crucial step in preparing data for density-based clustering. Proper preprocessing can improve the quality of clustering results and help identify meaningful clusters. Some important preprocessing techniques for density-based clustering include scaling and normalization. Scaling involves transforming the data so that each feature has a similar range, which helps prevent certain features from dominating the clustering process. Normalization, on the other hand, involves transforming the data so that each sample has a similar distribution, which helps ensure that all samples are equally important in the clustering process. To preprocess data effectively for density-based clustering, it's important to carefully select and apply the appropriate techniques. Experimenting with different preprocessing techniques can help identify the most effective approach for a given dataset. Density-based clustering has several applications in machine learning. One of the most common applications is image segmentation, which involves partitioning an image into multiple regions or objects. Density-based clustering algorithms, such as DBSCAN, are effective for segmenting images because they can detect clusters of different shapes and sizes. Another application of density-based clustering is anomaly detection, which involves identifying unusual data points that do not conform to the expected patterns. Density-based clustering algorithms can detect anomalies by labeling data points that are not part of any cluster as noise. An example of this is credit card fraud detection, where anomalies in credit card transactions can be detected using density-based clustering. Real-world applications of density-based clustering include vehicle tracking, customer segmentation, and gene expression analysis. These applications have benefited from density-based clustering's ability to handle noise and its flexibility in detecting clusters of various shapes and sizes. Limitations of density-based clustering. Density-based clustering is sensitive to the choice of parameters, such as epsilon and minimum points, which can lead to suboptimal clustering results. Density-based clustering is not well suited for high-dimensional data, as the curse of dimensionality can make it difficult to define the notion of density accurately. Density-based clustering can be computationally expensive, especially for large datasets. Tips to overcome limitations. Choosing appropriate parameter values based on domain knowledge and experimentation can help improve the quality of clustering results. Preprocessing techniques such as feature selection and dimensionality reduction can help to reduce the dimensionality of the data, making density-based clustering more effective. Consider using parallel or distributed computing techniques to handle large datasets more efficiently. Density-based clustering is just one of many popular clustering techniques available to data scientists. In this slide, we will compare density-based clustering with other commonly used techniques, such as k-means and hierarchical clustering, and discuss their relative strengths and weaknesses. K-means is a centroid-based clustering algorithm that aims to partition the data into k distinct clusters based on their similarity to each other. It works by iteratively moving the cluster centroids until the within-cluster sum of squares is minimized. K-means is fast and efficient and is best used for data sets with a small number of dimensions. Hierarchical clustering, on the other hand, is a more flexible clustering method that builds a hierarchy of clusters. It can be either agglomerative, where each data point starts in its own cluster and is gradually merged with nearby clusters, or divisive, where the entire data set starts as one cluster and is recursively split into smaller clusters. Hierarchical clustering is best suited for data sets where the underlying structure is not well known, and the goal is to explore and visualize the data. Density-based clustering is a density-based algorithm that groups together points that are close to each other in space and have a high density of neighboring points. Unlike k-means and hierarchical clustering, density-based clustering can handle noise and is flexible in detecting clusters of various shapes and sizes. However, it requires careful parameter tuning and may struggle with high-dimensional data. In conclusion, the choice of clustering algorithm depends on the nature of the data and the problem at hand. K-means is suitable for low-dimensional data sets, hierarchical clustering is great for exploring and visualizing data, and density-based clustering is useful when dealing with noisy, high-dimensional data sets. Choosing the right clustering technique can greatly impact the success of your project. It is important to consider factors such as the nature of the data and the desired clustering outcome when selecting a technique. For example, k-means clustering may be appropriate for datasets with a clear number of clusters, while density-based clustering may be more suitable for datasets with irregular shapes and sizes. Additionally, hierarchical clustering may be useful for identifying relationships between clusters. Consider the following questions when selecting a clustering technique. Is the dataset continuous or categorical? How many clusters are expected in the dataset? Is the dataset large or small? Are there any outliers in the dataset? Are clusters required to have similar sizes or shapes? Answering these questions can help guide your decision in choosing the appropriate clustering technique for your project. This code applies DBSCAN clustering to a dataset called data.csv, which has two features. The standard scaler is used to preprocess the data before clustering. The DBSCAN model is defined with an epsilon, EPAs, of 0.5 and a minimum number of samples, min_samples, of 5. The fit_predict method is used to cluster the data and assign each point to a cluster. Finally, the clustering results are visualized using a scatter plot. You can modify the code above to suit your specific use case and dataset. Make sure to adjust the parameters of the DBSCAN algorithm according to the characteristics of your data and experiment with different preprocessing techniques to improve the clustering results. Density-based clustering can also be used in city planning to identify clusters of similar land use patterns or population density. By analyzing the local density of certain features such as residential areas, commercial zones, or green spaces, city planners can gain insights into how neighborhoods are structured and how they relate to each other. This can help inform decisions related to zoning, transportation, and urban development, leading to more efficient and livable cities. 1. Zoning. Density-based clustering can be used to identify areas with similar characteristics and create zones for different uses, such as residential, commercial, and industrial. To transportation planning, density-based clustering can help identify areas with high demand for public transportation, leading to better planning of transportation infrastructure and services. 3. Land use planning. Density-based clustering can help identify areas with high demand for green spaces or community facilities, such as parks, schools, and community centers. 4. Demographic analysis. Density-based clustering can be used to identify neighborhoods or areas with similar demographic profiles, such as income, age, or ethnicity, which can inform planning decisions related to housing, employment, and social services. 5. Environmental planning. Density-based clustering can help identify areas with higher risk for environmental hazards, such as pollution or flooding, and inform decisions related to land use and development. In conclusion, density-based clustering is a powerful technique that can identify clusters in data based on their proximity and density, making it particularly useful for datasets without a clear structure or shape. This technique has several applications in machine learning and artificial intelligence, including anomaly detection, image segmentation, and recommendation systems. By implementing density-based clustering algorithms in Python, we can analyze data effectively and obtain insights from the clustering results through visualizations. However, it's important to keep in mind the limitations of density-based clustering and choose the appropriate clustering technique based on the nature of the data and the desired outcome. Overall, density-based clustering is a valuable tool to have in your data analysis toolkit. Thank you for watching this video, and I hope you have better understood density-based clustering and its role in city planning.